Okay, so today, basically, I'm going to talk to you guys about things I've seen in the semiconductor industry over the past 15 years. I've reverse engineered several hundred different devices over, from the early 90s till today. Actually, it's almost 20 years, I guess, but who's counting? And so I just thought I'd sit down and show everybody like some things that I've come across, meshes, things like this, before the meshes, the way things used to be into the way things are today. And it's interesting because things haven't changed that much, but they've changed enough that it is different. But yet, if you're involved from it on a daily basis, you realize that it's not that much different, but it would look at from the outside, the introduction of the analysis. So you get involved in it, and then you realize it's not much different than it was, but it's smaller. So at the end of the slides, I'm going to go through some slides with you guys, and then when it's all done, I was told by all you guys last night that you want to see porn. So I have about 100 gigs of it, and the drive's right here, so we can, and not really porn, but chips. So okay, I want to thank you too for coming this late in the day, because it's been a long day for a lot of us. So, and at the end of this, if you could fill out your feedback card, because Blackhat, I never get any feedback from these talks, and so I know I'll forget to tell you at the end of this. So I wanted to tell you at the beginning of this. So who here works with semiconductors? Everybody almost? Okay, embedded smart card or just like microcontrollers? What kind? What kind? Somebody? You design them? You design microprocessors? ASICs, nice. What process do you guys use? No, not the fab, but what size? Like 90 nanometer? Nice. So today I'll take you to 90. That's as low as we're going to go. We could go to 45 or 32, but I have never seen a smart card that low yet. But I'm sure they're going to come sooner or later, because everybody uses, like you said, they're fabless, a lot of these places today. So they're going to TSMC and TMC, and they've got the process down pretty pat. So in the past, there weren't really any security challenges. If you could put a needle on the bus, which was humongous. We're talking over a micron. In the 80s, things were 3 micron, 10 micron, NMOS, PMOS. Things weren't even CMOS back then. And so the geometries were so huge, you didn't even need things like what I'm discussing here below. A probe. You needed a probe station, yes, but you didn't really need an optical microscope. You could use a good optical microscope. You could use a very cheap dark field type microscope, because the wire sizes were humongous. Any wire size that was above 1 micron, you didn't even need a laser cutter. Laser cutter is going to be good from about a large scale chip above a micron down to about 350 nanometers if the wire size has some space. In other words, if there's some separation between the track. If their tracks are tight, your laser is going to probably short 2 tracks out. So back in the 80s and the 90s, you could get away with a very cheap probe station. Who here saw my DEF CON presentation in 2008 where we probed a bus? Okay, we put a single needle on the data bus. I think it was D0, the least significant bit of an 8051. And with one glitch, we made the loop repeat 256 times to spill RAM or to spill the Infineon CMS, some extra datas. And so that was a makeshift probe station. I used tape to hold the micropositioner in place, and then I used Velcro for the actual the landing area to hold that down. So you can make things out of anything almost to work with the old stuff. So anyway, I don't know if you're aware of this, but most people out here that read these data sheets, they trust the manufacturers. So ST tells you, we run on the internal clock. We never begin on the outside clock, and we scramble. The bus is scrambled. Fetches are encrypted from ROM, or et cetera, et cetera, et cetera. Half the time, this is BS. It's smoke and mirrors. And I like to say they're peddling snake oil. And I said ST because ST is famous for this. ST today will tell you that they've encrypted their ROM, and really what they've done is they've done an XOR against a static pattern. So depending where your high address is in the physical fetch, depends which XOR byte you're going to exclusive or the fetch against. A lot of these companies will tell you something like Infineon. They're famous, Siemens Infineon back in the 90s, even today. Due to ROM implantation via ion implantation, ROM not visible. Well, guess what? Anybody here ever heard of a Dash-Etch stain? No. So Dash-Etch stain is like 1 part hydrofluoric, 1 part nitric, and like 8 parts of acetic acid. When you put this down on the substrate, on a delayered substrate, it accents the P-type dopings, so they change color. And this takes a lot of practice, and it's not something that I normally do because I have other ways of reading the ROM out. But invisible ROMs can be made very visible, very easily. The security on these chips is usually very simplistic to bypass. Today, in the past, they used microcode. Everybody ran on PLA or microcode table. In fact, a lot of them gave Intel a copyright logo imprint saying, copyright Intel 1978. Right there, boom, 8051, if you didn't know what it was. Today they run on, most of the time, pure logic. So it's a pure logic implementation of a CPU design. And it's good, but it still needs improvement. And we'll get into that a little bit later. Does anybody have questions so far? I don't know why, but every time I speak, I'm very nervous. So I'm losing my thoughts. So anyway, okay. So what makes a device secure? Anybody? Okay. Masked or implanted ROM, contents. Lack of public documentation half the time. They try to control it. Maxim Dallas controls their documentation for their DS2432, their 28 series one-wire devices, for example, their SHA-1 authentication parts. Every smart card, you have to sign an NDA to get the documents. Philips NXP has these for their little transponder ICs. They basically try to control the distribution of the documents, and therefore, I guess it adds a level of security, and it does to a certain extent. But it's not, if I can get these documents when I have no business having these documents, then obviously that's not a direction that they should rely on. They don't typically use a standard bootloader to load these memories. For example, it's a masked ROM or it's an ion implanted ROM, as I stated above. So that means that basically you do your design, you simulate your design, you feed it off to ST or whoever it is, and they produce a mask, of the chip for you. The bootloader, if it's like a flash-based MCU, is customized to the password for you, the customer. A lot of these times, these chips end up on the surplus market of like hkinventory.com, hongkonginventory.com, and you can pick up these devices for as little as 15 cents. Did anybody see my talk online from Blackhat in either Spain or DC this year with the TPM hack? So I bought, I think, like 200 SLE 66 and PE Infineon chips from the Hong Kong inventory for, I think it was like 15 or 30 cents each, very cheap. And I recently received 243 pieces of a Thomson TPM device. So I think Thomson will be next, but we'll see. So what do you guys think? This is an off-the-shelf micro. Is it secure? Because I just want to give you guys some examples here. Like, here's an Atmel. This is an 18 mega 2560, so 2560. It's got 256K of kilobytes of flash. It's got some EEPROM, and it's pretty nice. I mean, do you guys think it's secure? Nobody? Okay. Well, you have to wait till the end. So, in the really, really old days, you could literally see the ROM bits on some ROMs if they were masked. It just depends what metal layer, how they designed the ROM, and what metal layer the ROM bits were visible on. So here, you can see in this picture, I can read this out like a book. In these columns, let me open this to a larger picture. This is an Oki Data 8051 from like 1985, but it's just to give you guys some examples here. So out of view are the column decoders, and basically all the D0 bits of this ROM come out of the first. There's 32 across, 32 of these small T's, and so every 4 T's represents 1 bit weight. So these 4 T's. Let me see if I can highlight this. Everything oops, hold on. Everything from here down basically represents D0 depending what address you're at in the ROM. And then everything on these next 4 represented D1, and then so forth across it. But as you can see, using a technique called, on an optical microscope called dark field, I can bend the light in such a way that it actually accents the ROM bits. And so you can see clearly, I don't know which way it went, if a solid was 1 or a solid was 0. It just depends how the ROM was designed. But with today's computers, you can just translate this table any way you want to, and you can play with it in software to figure, to understand, it's an 8051. So your software can deduce what these bits, flip the state that you recorded it as or don't. And so it's pretty cool. Good old Sky period 7. Anybody here from the UK, from England or Europe? Anybody here into like satellite television from over there in the past? So in like 1992, a company called NDS out of Israel, who I used to work for, produces this chip for Rupert Murdoch's Sky broadcasting system. And so this is just to give you an example of a secure smart card from 1993, 1991 maybe, where's the security, really? Because the only thing that made this secure was the fact that it had a mask ROM. So that it means that NDS designed the ROM, simulated it, sent it off for production by Motorola. This was known as whoops, hold on a second. This was known as a 68HC05 SC24. It's basically any chip that they produced that had a masked ROM and no type of bootloader to load it was called an SC series. And they made several different ones. So you had 5 major pads on this chip. Let me open it again, large. And you guys are welcome to all these pictures. I'll zip them up, and when I return home, I'll throw them up on flylogic.net. And if you want them, just I guess email me, and I'd be more than happy. So you can see here clearly the bond pads, but there's extra bond pads. So I don't see the security here. You've got this is VCC, this is reset, and this is your clock. Now these pads are abnormal, and I think it's because they assume that the people that would actually aluminum wedge bond this package were retarded or something, because I don't understand why they make different pads than the others. But they've brought pretty much the whole bus of the internal outside right here. So all of these pads were technically, if you rebonded them out, you could see the whole program memory running in the outside world without a probe station. So. And down here you have the ground, and you've got the I/O line. Very basic smart card from the old days. This chip got hacked very fast. Everybody was watching Sky for free, and these were good times. Now I don't condemn it, but I don't promote it. So it was gray there though. It was, couldn't get a subscription, but the signal came in their yard, kind of like Canada and the States. So you can see down here. And I'm jumping around because half of you guys have never even seen a chip possibly. So I'm trying to go slow and take this from the beginning to today, the early days till today. So, but what you can see here, what you're looking at here, are basically 8 instruction register latches. And so basically these work like a 74 HC 573. Anybody work with that type of a TTL logic device? Yeah. So you have a gate that controls the latch, and it's transparent when it's high, and when it goes low, it holds whatever value is presented. So you can see the data bus is coming in here. Give it a second here. This is an SSD drive, and it's so slow. So right here, you've got the data bus coming in, and you can see where the via is plugged down. You got 0, 1, 2, 3, 4, 5, 6, and 7, 8 bits. So in theory, if you sit on this, this is where you'll see the actual opcode being fetched, and you'll see some of the data bytes too. You won't see all of them though, because of the way the von Neumann architecture was designed into this. And so, if you think about it, you can use 2 needles to dump this chip. Anybody have any ideas how? Anybody? You can use one on the latch gate clock, and you can use one that walks the data bus. So you put 1 needle down on the latch, and when the timing's right, that you see an instruction that says like fetch your opcode, and then the next clock cycle it says fetch your next opcode. It's Perfect. So in 2 clock cycles, you get 2 opcodes fetched. Now, that's not really the case on the old 6805s because they had to divide by 2, and I don't think any instructions ran in 1 or even 2 clock cycles. But you could definitely get an instruction that ran in, say, 3 clock cycles. So then you get this pattern when you spill the beans that basically is opcode, opcode, space, opcode, opcode, space in basically a linear rip, a sequential readout. And this technique still works today, what I'm talking about. I mean, there's really no way for these guys to prevent someone like myself from breaking into their chip and hijacking the entire virtually mapped code space, let's say 64 bits, like a standard architecture, and making it just spill itself to me. Questions? Okay. So we have 58 minutes. Keep me in check or I'll never get done. So go a little later in time now. GSM says, well, we want you to make some changes. Motorola says, well, we actually made some changes for NDS for the Sky Period 9 card. Now, I'm not showing you a picture of the Sky Period 9 card, but just assume it came out, it got hacked, and it had an opcode swapping going on. So it was a little more tricky than just sit on the data bus and understand it. You sat on the data bus and you saw, for example, like a 49 instead of an opcode of a 29. Things like this. I forget the pattern, but so you had basically a swapping of bits and then an XOR on bit 7. I'm sorry, an inverse, of bit 7. And so if we look at this picture, they did the same thing. They did the same thing here, but no XOR on bit 7. So here's the data bus again. If we were to assume, am I going too fast? Everybody following? Okay. And there's value to what I'm explaining now that you'll find out soon, very soon, because this is really classic and it's awesome. It's old, but it's cool. It's very cool. And this is something that you guys, if you're trying to learn, can play with at home or in a makeshift lab or in college or something. I play with it at home. So basically, let's assume that the bus runs 7 down to, or 0, either way, 0 to 7, 7 to 0. Let's for ha-has, this is 0. This is 7, 6, 5, 4, 3, 2, 1, 0. This line is actually the clock line, which I don't know why it's there, but it is. So look where the via is. 1 second. So the bus is running, like I was saying, 7 down to 0. Now let's assume that these latches run 7 to 0 also. So what just happened here? If this is the case, then this via should have been up here on 7 here. It's not. Look what they did. They plugged it down onto bit 2. So that means that in order to understand the instruction set on this chip, you're going to get opcodes that you have to demangle, and then you're going to get operands, the second fetch, let's say, second or third fetch of an instruction that are going to be in the clear. Because the ALU doesn't do this. Only the opcode does this. This is a very beautiful way of keeping honest people honest back in the day. If they just tried to sit on the bus, at the exit point of ROM, let's say, they're not. And given it's a von Neumann architecture, this guy would be smart enough to know that he's going to see RAM and he's going to see ROM and EEPROM all on one data bus. They didn't split these up in the old days. Everything fit in 64K. But what he would have seen was basically that. Every time it's bit, the opcode is really bit 7, he's going to see that it was bit 2 that came on, and so and bit 7 was really plugged into bit 6, bit 5 was really plugged into bit 0, and it just you can kind of see the pattern here and so forth. I was very surprised when I saw this because this is off-the-shelf GSM SIM chip from 1996, 1995. These are very large chips also. These are at least 1 micron. I've never measured them, but if I was to measure them based on the top metal track, I'd say that they're even maybe 1.2 microns or bigger. So another company out there making smart cards for DirecTV. Who here has DirecTV? Anybody? Okay, so I used to work for them, well, NDS, and so we made this custom chip here. Well, this one wasn't custom, but it had an ASIC with it. So Sky 10, anybody know Sky 10 in the UK? So Sky 10 gets this chip with an ASIC. Americas gets this chip with an ASIC. South America gets this chip with an ASIC. This chip's being used all over the world. They tell Siemens, we want you to swap the instruction table because this chip ran on a microcode, and it was more like a RISC infrastructure, and it simulated the 8051. So you had a ROM here that was not visible without staining. So in order to see the bits, the ones and the zeros here, if you could, you'd have to stain it with the dash etchant, and then you'd see dots everywhere there was a p-type doping. And so you could do it that way. You could stain it, and then if you figure out the ordering of the addressing scheme, you'd have the entire ROM read out, but you still need to get the EEPROM out. And so NDS knew that you might sit on the data bus and eavesdrop. And so what they did was they told Infineon, it was Siemens back then, we want you to take the instructions, which are mapped through this table right here, and we want you to switch them around. This is a table basically of 256 by 9 bits. So basically, it can go from 0 to 512 in theory, like a high and a low address, and it supports 256 opcodes because there's 256 opcodes in the 8051. So this table's readable, and this table's readable optically. They knew you wouldn't understand it, because in order to understand where this points into here, you would have to understand, all of the logic over here. And obviously, the easiest way for a hacker to get them would have been to read the ROM optically. But again, why not just sit on the instruction latches, freeze them, and make it spill its guts? You'll have everything out in 10 minutes. So does anybody do probing, microprobing? Cool. Do you play around with like freezing instructions and things like this? No? Okay. You can have a lot of fun with it. And these chips are great to learn on. And any CPU really you can play these tricks on. So you had the ROM up here, and then you had the static RAM over here, 256 bytes, very basic. You had the program counter over here to drive it, the high and the low, and you can almost literally see it too. I don't even think they scrambled it. The low order bus, I don't remember which one it was, but it's either the high side or the low side of this area. Your picture looks better than my picture. So here's your program counter basically to assign everything, and so here you've got instruction latches. It's not a very close-up picture, but this is 0.8 microns, so this is 800 nanometers. The gentleman back there, I think I heard him say 45 nanometers. I believe that's what you said. This is 800. So this is night and day difference. We're slowly shrinking in this presentation, just FYI. So we'll be at 90 in about 50 minutes. So the opcodes basically were presented, read from the bus, came in on these 8 latches and presented. They're latched here to be presented to this table. Now at DEF CON, I showed you this table in 2008. I showed it to you where you could see this, at the poly you can see the actual ones and zeros of this ROM. But you've got to strip off this top metal first. And so here's your instruction latches. If you want to dump the chip, you can just freeze it right here and sit on it. And it's ordered 0 to 7. Even the bus was in order from 0 to 7. This is 0, 1, 2, 3, 4, 5, 6, and 7. What latches here is held and driven on these lines here up into the row and column drivers. And then the next clock cycle, the value is, well, actually it's combinatorial logic, so it's driven immediately. Anyway, so that's this one. So even Infineon got a little smarter. But I think it was NDS's doing that did this, but I never really got the 411 on who told who what to do here. But so Siemens gets smarter, and they said, okay, now what we're going to do for the Sky 11 chip. Anybody here use Sky 11? Okay, never. I'm going to stop asking then. So satellite hackers, Sky 11 chip comes out. This time what they did, same type of architecture. I think it's a 0.7. So they shrink from 0.8 to 0.7 micron. So they go from 800 to 700 nanometers. The bus is still in order. So 7, 6, 5, 4, 3, 2, 1, 0. Now, what's interesting about this architecture is that the low address of the fetch, or the low address of the program counter is on the bus. So you get the low address of the program counter, and then on the next clock cycle, you see the value that's being fetched from that memory address, or written to for that much if it's RAM. So you have the bits coming in 7, 6, 5, and all these in order. But look, there's some logic added in front of the latches. So if you recall, this whole block right here. This is extra, and what this actually is 3 extra latches to latch 7, 6, and 5 of the data bus, and then they took and they had 3 XORs. So what they latched the value of the low addresses 3 bits of the low address got latched, and then they got exclusive ORed against 3 bits of the opcode. It's very clever. It's very cool, but it's very obvious also. And so this chip also got hacked. Now, at this time, though, NDS knew, they started putting ASICs into the silicon. So they were having heavy-duty, opcode changes. The data bus was being scrambled, and they had an ASIC on board at this point. Now, this is still Siemens. They'd become Infineon like a year later or so. In Europe, there's a company called Canal Plus. Anybody know Canal Plus Technologies? So Canal Plus Technologies used to only be television producing. And then at some point in time, they started coming out with their own conditional access system called Seika. So Seika Generation 2 they had this belief that they could use several different smart card chips. And through this several different launches of smart card chips, they'd somehow be secure. But you're only as strong as your weakest link. And so they introduced for Seika 2 this Okidata 8051 type architecture. And it's kind of funny because Oki added a bunch of fake tracks to the chip. And ST is famous for doing this too. They add a complete block of logic that's fake, that has nothing to do with anything. And so you can see here's a line. This line does nothing. This line's just sitting here floating. And I guess they think they're protecting you from optically reading the ROM out again. But who's going to optically read out the ROM? That's something that I would do today more than I would have done in the past. Just because it's easier for me to image the ROMs today than it is to probe the bus, because they've gotten so small. So you can see here, this is all fake, and the chip wasn't handled very good, so it got scratched here. So I don't understand why they did it, but this is a technique that they started to come out with. So here, this is the entire chip, and as you can see in the image, it looked pretty cool. I don't know otherwise what it did, though. So, I mean, now today, actually, let me slow down here. So here's the core of this chip. It's so obvious in the older technologies where the core was, because the core ran on I always call it microcode, even if it was a PLA. Does anybody design CPUs? So you know exactly where I'm coming from. This table has to know what opcode you're executing. That means the instruction latches are near. So you see a ROM in the core, there's something important there. And so it's first, this will stick out like a sore thumb to anybody. Anybody that's got, that understands what they're looking at or tries to. And so I actually don't know where the instruction registers are, but they're over here. So I mean, I never actually probed them. That's why. So what you'd see on the instruction register, I talked about it earlier. You'd see the live data bus on the left side, and on the right side, you'd see the frozen instruction of the opcode it's executing. If it releases that drive and becomes transparent, that opcode's not going to execute if it's in the middle of executing something. And this depends on the design too, the architecture. So now we're moving up more and more. ST, aka SGS Thompson, they're a French company. They came out with some pretty cool chips, and I actually really like these guys. So they've been making 6805 since early 90s, 91. They started with no mesh, and then they went to a chip with a mesh. And the very first mesh was just simply a plane, and on the plane you had little holes in it. And I didn't take the time to show you that just because it's too easy. It doesn't really show much. There was a metal plate over the whole chip basically with holes in it. And so in the wired video, did anybody see my wired video where I take the nail polish and make the mask? Good. So if you look at the wired video, you can see clearly that type of a mesh. And I will show you some pictures of it after when we're all through with the slides. And so this chip really, what made it secure, I guess I didn't link to it. What made this chip secure was that you had a mesh that had an active sense line, like a snake, and then it had ground, which are true grounds coming from this side and this side, but they didn't meet. So at this end of the chip, the grounds are all connected on the corner, on this corner, so to speak, and then they're going diagonally across the chip, and then from the opposite edge, the same thing. And in between this, you have this one wire that is tied to VDD, the VCC line, 5 volts, 3 volts, whatever the chip's input is, and it's weaving through it. If this line is broken, it would freeze the core. That was the only punishment on an ST16, was that the CPU stopped running. So it was kind of interesting because you knew exactly if you fixed the mesh or not, and when you were all finished, you could simply just, the chip's running again once you patched it. And that's exactly, actually that's not exactly what I did in the wired video. In the wired video, the mesh, because it was just a solid plane of ground with holes in it, I made a big hole in it and I was just able to probe the bus. I didn't even need to fix the mesh. Today, as we start to shrink, we go lower. That last one was 1.2 micron, jumping around a little on the size back there, just to give you some ideas of what I've seen. Today, these chips everything I see today is below 350. It's typically about 220 if I had to average it. Some are 90, some are 180, some are 140. It just depends who makes it. But the principles that I'm describing about the instruction register and stuff still applies today. Even the nail polish attack. I'm going to show you some chips from Thomson that are 180 nanometers that I executed the nail polish attack on. And I stopped early because I ran into a problem with the nail polish coating because of the heat. The heat cracked it and it came off. And so before I go too far off topic though, so some of these smart cards and such come out with filler metal. You can see it here. This is TSMC. I believe it's like a 250 nanometer process. I've never really measured it, but it's smaller than 350. And so, actually it may be 350, I'm sorry. It may actually be. So this chip, this is not security. You don't lay filler metal here that does nothing and call it, it's obscurity, I guess. It's obscuring below, but it's by no means a security, enhancement to this design. And if anything, it helps me because when I'm in the fib, I can count. So I can count from the edge and say, okay, I got to go over 18 of these little stubs and then drill. And it gets even better because look here, they have these little I don't even know if these are alive, but there's it came up to the metal 3 surface and then it went for a few micrometers and then went down again to metal 2. And I don't know what these little stubs are doing, but if they're, I'm assuming they're live. And so I can measure off these stubs and say, okay, from the stub, count up 5, go over 20. Anyway, so this is, if you use TSMC in your chip, and you tell, they give you this black box of a memory. This is one of their popular memory sizes that I see. I see Freescale using it. This is some Chinese smart card that use this one. And you can see fillers everywhere, but there's no mesh. This is the top metal right here. One of these lines might even be important. So I may not even need to fib it, because if this is 350, I believe it is actually 350, and even if it's 250, I can still hit this track right here. It's by itself. And I can still hit this one right here, and I can probably get to these two because I'm pretty good with the laser. But if I'm skeptical, I'll just go use the fib and open them. These you don't even need to count. You can go right to them. Take an optical picture, go load it in your fib, make sure you're grounded well to your stage, and then in 5 minutes later, you're looking for this wire once you've leveled yourself. So those not so invisible ROMs. Here's the case, 180 nanometer Samsung smart card. So Samsung has these smart cards that they produce. I don't believe they're common criteria certified or anything, but what's interesting about these smart cards is that they give you a bootloader. You sign an NDA to get the documents, and then they tell you, okay, when you buy the cards from us for whatever, $5 each or some price, there's a bootloader in a ROM, and the ROM also has, you can permanently disable the bootloader, and the bootloader also has ROM functionality for triple DES or RSA, some type of PKI, etc. The bad part is the ROM is visible. Now this, I didn't actually stain this. Oliver Kummerling, this was donated from Oliver Kummerling, so I want to give him some credit for this picture. So in this picture, he stained this ROM and all the P-type dopings came out. Now what's important about this is they didn't even encrypt the ROM. This is supposed to be a smart card, a brand new smart card fielded today, and yet its ROM is in the clear. So I don't understand that. Now I linked you to the wrong picture here. I'll show you another picture of this ROM later, and you can see clearly where the ROM bits went to FFs. Now this is an ARM 9 or an ARM 10 processor, and so when the ROM became empty at the end of the ROM, they were just all ones. And I believe on this ROM, a white spot is a 1. So. And in the SEM, this is a SEM image. You can clearly, it's dark everywhere that it's not light. So you can see, I mean, it's very easy to detect the bits on this ROM. Then we got baseband processors from cell phones. Anybody do like mess with cell phone hacking? So all you guys want to always hack the iPhone, and you always want to hack, the BlackBerry and all these other phones. And the initial way to get to this would be to look at the bootloader ROM first, because a lot of these guys, they might run encrypted code today, but a lot of them just had a signature. So they, it's signed with RSA 128 and MD5 hash. Well, that's great, but what do you do after the signature is checked? Do you ever check it again? So I mean, one wire and you can order yourself into a higher area of the flash, because the flash has sections that are checked. So how do you know this? You don't have the manuals. Well, you can read this ROM just like if it was textbook. But I mean, now I imaged it in the fib. This is done in a fib, so this is a fib image. But this ROM is not encrypted. If I thought it was, this gave it away that it isn't right here. Because if it was encrypted, this wouldn't have been all ones. So every bit here is basically unprogrammed in the ROM. They could have at least, and this is good advice for all of you if you design a software, or if you design hardware, it's good to think like this. This ROM should have had junk put at the end of it. This ROM should never have had static ones. And because it did, it's very obvious that it's not encrypted. Well, you could do it, but because the user software and your bootloader technically would never call it. Do you follow me? Okay, so that's what this gentleman answered the question. That's a good point, because I only see it from one side of the coin. But this gentleman's saying that the trade-off is basically that reliability issues in manufacturing. So thank you for clarifying. Understood. No, that's a very good point. So he's saying basically one error you might end up executing from this area, and it's junk. At least this case it's like a NOP or something in the ARM language. So, but you can read this ROM out like it wasn't even, like it was nothing to do. The problem with this chip is it's so small. I think it was like 130 nanometers. Maybe it had been larger than this. But no, it was 130 nanometers. The problem with this optically, 1500 mag, 1000 magnification, you can't see it clear enough to really make out the ones and zeros. You can, but it's grainy. It's so, I just imaged it in the fib. This is 5000 magnification. So zoom it in 5,000 times, and this is what those bits look like. I have no idea the way it's ordered. I just this is just to show you guys. So a lot of companies like Atmel are doing meshes. Anybody here design like this type of security product that has like a meshing over it? The mesh is great. The mesh slows me down for about a day. So no, and I mean this sincerely, it really does. When I talked about the TPM attack, I explained it took me 6 months. But what everybody didn't understand was that it took me 2 months to actually finish the TPM chip. It took me 4 months to make buffers to sit on a 1.8 volt signal without changing its capacitance so much that it shuts the chip down. At 33 megahertz, it's pretty fast to put down a bunch of needles, and so basically there were challenges on that, and also I had to come up with a way to get around the mesh. But once I came up with this way to get around the mesh, and as well as the other challenge that I just described, now those apply to any chip today. Now this chip's not that small, but what's neat here is that Atmel went out of their way. This is from a chip called the Crypto Companion. Anybody heard of that? Atmel Crypto Companion? Okay, it's snake oil, so stay away from it. So it's this chip. Let us do the cryptography for you. We'll prove to you that they authenticated correctly. Blah 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 blah. I say stay away. That's my humble advice. So anyway, but this mesh is cute. It's very cute. Another company making meshes like this is Renesas. Anybody use Renesas smart cards? If you do, there's a good chance that the mesh looks similar to this. Several circuits. And like you can see here at the top of the screen, this is several different circuits. But what the engineers didn't understand that designed this mesh is that I can cut one of these lines at a time and watch them go out and turn black. And this is called voltage contrast. And so as I cut the line, I can see everywhere the line went. Now I will actually have to polish down the die to where the metal's exposed. Otherwise, the fib won't show me anything. But once I've done that, as soon as that line floats over on one end, it's going to go darker. It's because it's not properly connected up anymore. And you'll see this in a little bit. Okay. Voltage contrast. It can kill you. You think, these guys are thinking, we've got it. No problem. Well, they don't really have anything. Because you can see here, this is from the 66. So here, this line, it's out here, it's out here. Everywhere I marked it in red, the line was out. Now, the 66 mesh, I really like it because it was consistent. So they get an A with me, if I had to rate them. Because even though it's simple for me to break now, it wasn't in the beginning, because this mesh covers the entire substrate except the bond pad area, and they're very tight line spacing, and it's consistent. NXP, Atmel, ST, I can't even count them, and you'll see why soon. But NXP and Atmel's meshes are not as consistent as this is. So, in conclusion, security is always going to be constantly evolving. I took you from the early 80s into today, and nothing's really secure. There's gentlemen here that gentleman that designs chips. He may learn something today, he may not learn something today. I don't know, but for one thing, he'll think twice before he does his next layout. And so this is good, because if you're using a chip from a company, you need to learn, the user needs to trust the vendor, but it's kind of hard to trust the vendor when you're not really sure what's inside. And I've made a lot of people angry in the industry, but I've also made a lot of people happy, because the manufacturers, like Infineon, probably hates me today because of the TPM break. And I didn't mean to do it to them in that way, but it was important to get that out to the public that, it's not as secure as you think it is. Who here uses an Aladdin e-token? Nobody uses an Aladdin e-token Pro? Aladdin e-token Pro runs on something called the CardOS. Anybody here use CardOS? Your application is stored in the EEPROM under the default key. You do? No? So the default key, so basically it's a 66 that has a possibility of having some random key into the EEPROM for the encryption of the EEPROM. The ROM is encrypted with a random key per mask, and the static RAM is encrypted with a random key that's chosen the first time it's serialized. Long story short, Siemens writes a CardOS operating system that doesn't even take advantage of this nice 64-bit X key, which even if it is in a way snake oil, if it's there, use it. And they didn't use it. So buyer beware. You should be careful, because the pin is in the clear on those e-token Pros. So do me a favor and fill out the comment card like I was saying. So who wants to see some porn? Yeah, come on, here. Okay. So. Okay, now you got to bear with me, because we'll get much better images this way. So I'll start with Atmel. I have a whole drive of images here. I have everybody. I don't even know who to start with. This is 100 gigs, but we'll start with what I planned for the talk. So we'll do Atmel first. These are in no specific order, really. So the Atmel Security VR, it looks like this. Now, this is a mesh that gives the appearance that it might be what I call three-dimensional. And so the reason I call it three-dimensional is because the mesh begins on, for example, hypothetically metal 4, and then it goes under to metal 3, and then comes back up somewhere else on metal 4 again, doing kind of a lane shift. But then it's static down the center. So Atmel missed something very important on this design. Well, one thing that I should mention is it's not a 3D mesh, because the mesh actually doesn't go up and down. It changes the size and the thickness of the track, and that's why you get this effect over here in the corner where it looks like something's changed. But if I zoom in on the next image, which is just the very top row, at a little higher power, you'll see that really this is just these. There's actually an error here, but these are these wires that just came over and then came down and got thicker, and they give the appearance of being some type of an arrow. So it gives a really cool look, but it's more of an obscurity technique than anything else, because as soon as you strip this with some hydrofluoric acid, you strip off the top metal, you can leave the trowel in the glass and the oxide where the metal lived, and so you can follow over where the track went anyway with it missing. And Atmel and most of these mesh companies miss the fact that I'm not going to remove the entire mesh. I'm going to remove a piece of the mesh, as I described in the TPM attack. So I'm going to find where the instruction latches are, and then I'm going to, figure out, okay, it's 100 microns over, and it's 140 microns up in the chip. You go to this location, and then you dig right there. You dig out some type of a known reference, as I described in February, and then that's the only area that you're going to bridge. Atmel Secure AVR. Anybody used an Atmel Secure AVR in the past? This is an older Secure AVR. This is a 350 nanometer. I think it's three metals. It's a nice chip. It's only flash with EEPROM, and then it has a bootloader that they load into their flash that you can overwrite later. It's got a crypto coprocessor, and when I first looked at it, I thought that this was actually some type of boot ROM. And so I analyzed it, but it wasn't. They were not AVR opcodes. It's some type of custom CPU that they've designed for crypto for their PKI, and so it's just kind of neat. Again, it's an image from the fib. So the 6464 looks like this. Now this is wrong. These were comments I made in the very beginning, and this is not a bootstrap ROM, or a bootloader. What this actually is the crypto ROM, and this is what it looks like, before it's stripped down. And then the other picture you saw was when it's been delayered to the very bottom of the chip, basically. The instruction registers, Atmel they've missed the boat here. So Atmel thinks, that we've covered the EEPROM and the flash because they're under this. So if you want to, they're going to probe this, and they're going to tell you we've encrypted it and we've buried it under metal. So get through it. Well, guess what? I can get right through it. In fact, while I'm on this topic here, I'll open another folder. Give me 1 second. I think these are the holes. I was playing around with UV one night a long time ago in 2003. And here's an example. So much for that ground plane that it might even be VCC. I have no idea, but it's probably grounded. And so here you can see this chip still ran when I was finished. So here I used a laser, and I used it with green. Anybody here ever work with laser cutters? This is where they come in useful, even if it's like smaller than 350. You get solid planes of metal like this; they're perfect. And so here I used UV, but it wasn't good enough. So then I used green, but it was too low of a power. So here I used green, and then I used UV to finish the job. And then I actually hit these two power planes, VDD or VPP. I guess it's VPP, and probably ground or something inside the chip, and I put a needle on it. And this was just like a proof of practice, So these techniques are very important. You learn, like I might show you something that's on a 1990 chip, but if you think about it, it's probably usable still today. So this chip, you look at it and you're like, well, where are the instruction registers? So does anybody have any idea how to find them? Anybody? Come on, somebody. Castanol. Jawohl, but this is an AVR. It has 16 flip-flops of the common clock. So basically we start to strip the chip down. We strip it layer by layer. Top metal, strip it off. Actually, one of them you're going to leave it alone. Maybe you'll polish it down a little bit, to get rid of some of the passivation. Sometimes the die will look clearer in your images if you mill it for a little bit on a lapping machine. Just lap it down a little bit. Remove a few microns of the passivation, that very top oxide. So you strip this down layer by layer, and then you do photomosaics of the areas where you think they might be, and you're looking for some flip-flops that are going to have a common clock. Now these flip-flops are not going to be in the middle of this. They could be, but they're probably not going to be, because what you've got an instruction register here that has to decode and trickle out to decode every instruction the AVR has. And there's like 133 instructions or 132 instructions in an AVR. So the instruction registers or the instruction latches, depending how they've designed it, are going to be somewhere near the edge typically. And this is not for sure 100%, but I will almost guarantee you'll find them quickly if you look near the edge. But Atmel brags in their toes, the common criteria evaluations, that this is all encrypted. So even if you sat on the EEPROM or the or the RAM, or any of these RAMs, you're not going to understand anything because everything's encrypted. But what they don't tell you is encryption to them is a few bit swaps, some inverses, and an XOR, things like this. It's really silly today. I mean, no one truly is doing real, true, hardcore, DES decryption. And really, if you think about it, how can they? Because you're dealing with, let's say 4-byte fetch. That's the max, pretty much, you're going to deal with on an 8-bit CPU. 4 bytes are fetched maximum for some instruction. Typical instructions, 1 bit. And also, you have the trade-off of time. How you can trickle through logic, and it adds a propagation delay to the circuit, and that becomes your maximum clock frequency you can run at. But to really do like 16 rounds of DES, it's not happening on any of these small processors. So here, if you look on the side, Atmel talks about 72 lines coming out of the chip for debug testing. Well, these 72 lines are right here, down on poly. So Atmel says, you can't get to them anymore. We've sawed them off the wafer after production. Well, they've sawed them off. They're right here. Then you can get to them with a fib. But if you follow these, they come to what is basically a mux. And so at one of these lines that had a pull-up on it actually determined if you were going to run code from the outside world or run code from the onboard flashes. And this is how Atmel serializes their flash for the first time to install this bootloader. Because how else are they going to get it in unless they're probing the die? But there's metal. The top metal is covering the entire surface. So they come up with this really cool idea, but it was a really bad idea. Because guess what's near these lines? The instruction register. So right in this area is the Atmel 3232, 6464, 7272, C, whichever version of it, whichever flavor. Find this area, and right in this area from the edge will be your magic 16 flip-flops. The irony here too is, look how close to the edge you are on this chip. Every chip, you're always near the edge somewhere. And everything on this side of it everything down here has to do with EEPROM and flash encryption. Everything here on the side has to do with decryption of the fetch. The opcode's decrypted, and then it's latched. Does anybody have questions? Can I say that, please? Show you one where I've what? I've never failed. That's things. So, say again?
What about Deathfire and the new NXP pretend to be high secure chips like the Deathfire 8?
I've never seen it. I don't know. But I have Deathfire chips from back in the old Crypto One era when Dr. Knoll was working on it. And so I have frozen Deathfires that are on like 250 nanometer process. But with a SEM or a fib, it doesn't matter how small they go, you're still only as secure as Metal 1. So, I shouldn't say Metal 1 even, I should say the width of the track. So the chips, they can go to 10 nanometers. I don't care, I can still see it, and I can still touch their metal. Their metal tracks will never be 10 nanometers wide. That's the actual gate. And so the metal tracks typically are 300 nanometers, 400 nanometers, 500 nanometers, and up. Any smaller, I haven't seen. What do you know your track width on like a 45 nanometer process? No, it's going to be small, but I have a feeling it's going to be at least 100 nanometers. I've just never seen one to really compare. So here you can see now these bits were figured out because I know I've been into computers since I was like 9 years old. So I've had a computer since like 78, and basically I've written in like every language you can think of. Except the ARM, ironically enough. It's so popular. I know it only as much as I need to. But so I love the AVR. I love it a lot. And so you have to know the languages of these chips. That's something I didn't say before. So knowing the language of these chips, you learn to recognize the order the bits should go. Now, this was completely randomly placed. And, so bit 6 ended up here, bit 7, bit 1, bit 5, bit 10, bit 0, bit 8, bit 11, and it's just you have to deduce it. You have to study it and look at it and take it out. Take a run. And honestly, on a 16-bit processor, it's a pain in the butt. It really is. And there's other challenges too that I'm not even going to get into, like internal clock, when they come out of reset staying in sync, things like this. But what I want to show you about this picture that's important to me is I've written all over it, but you didn't see it yet. That's why I opened it in Photoshop. So we got an ugly poly layer here. So use nice tools like Karsten Knoll's D-Gate, things like this, and you can study the flip-flops pretty easily, or you can find them on your own. I try to use D-Gate, and I don't have success really, but we're going to work on that. So you can see here you've got a bunch of flip-flops, but these flip-flops are different. They're very unique in the architecture. Now, finding these took a while. It probably, I would say, took like a month. But this is the first time that I went after something like this. So it's tricky. So that's poly. You get your metal 1. Now you have your metal 2. And then if you want, you have ugly metal 3, but I'm not going to turn it on. So now you start to add things. Now let's add D0 trace. There's the D0 trace. So D0 on, off. You can see it. Now if we do turn on metal 3, and now you follow D0, look at that, it's coming out on top metal. What if I told you that every one of the data bus bits comes to top metal? You can hit this chip with a laser. You do not need a fib to attack any of those older Atmel's smart cards. When I told Atmel, they laughed. They said, oh, that's old. I said, it doesn't matter. You're as strong as your weakest link. This gives me an indoor to the AVR architecture that today's platform is built upon. So they don't just make something from scratch. Yes, they do, in the very early days. And then they build, and they build again, and they build again. They don't knock the house down and start over. And so you learn a lot you learn a lot by studying their older technologies. But anyway, all the traces came up to top metal, and you can turn them on, and it's pretty wild. Let me zoom out. So as you can see. So I really wonder, I hear these guys all the time that they say, oh, VideoCypher 2+ can't be hacked, and Nagar 3 can't be hacked, and DirecTV can't be hacked, and blah, blah, blah. And anything can be hacked with enough effort and someone that's motivated and focused. And I'm not saying that DirecTV or Nagar or anybody's going to be hacked, but they could be in theory. They're not as strong as you'd think they are. That you think they are. So we go back to this General Instruments chip. Anybody familiar with the GI VideoCypher system? So it got cracked back in, I guess, the early 80s. And then they came out with the 2+. Never got cracked, at least not that I'm aware of. And I don't know why. I really don't. The chip might have been custom, but it was some type of a TI MSP4, like a TMS 370 type chip. And so you look at it, and you've got some non-volatile memory here. You've got some static RAM. You've got more static RAM. And then here's the core, and look what we see here. What's this? Who can say what this is? I discussed this before. Micro or PLA, one of the two. So it's instruction registers are somewhere in this area, and they're right here. So there's your 8 registers. Freeze the latch, dump the whole chip. And then there's I think there's probably some other challenges. There may be an ASIC in here too. I don't know. But the chip's geometry was humongous. And the guys were cocky too. They put a little rocket ship on it. So it says Team Bonsai. It's funny, some of the things you see, ST puts frogs on all their chips, and these guys put, Team Bonsai. So, and if we zoom in a little closer, I just wanted to show you the Bonsai logo a little bit closer. But what's ironic here is I can tell that this is made by TI. This looks exactly like the older TI chips. You can tell the footprint, the way the process is laid, who makes the chip. Like I can spot TSMC any day, any time on like the 250 nanometer process and the 350 nanometer process. And it's interesting because once I study their flash on one, it's the same on the others that use that same type of flash. Maybe it's 16 bits though instead of 8 bits. It just depends. So here's a 200 power resolution image of the instruction registers. So you have 8 flip-flops sitting right here. You have one here, and there's an output here if you can see it on the screen. Here's another one. Now can anybody tell me what they see in this image? There's something weird about this image. Anybody see what's special about this? There's metal. There's a top layer of metal put over this area. So this was done on purpose. These guys knew that this was a weakness in the chip. And so they covered this on purpose. So you can't get to it without digging a hole through it first. So these were very early methods of protecting what they deemed a valuable area of the chip, sacred area. And here you can see one of these is like set and reset for the flip flop. And so you just check them, and the one that's holding the opcode when it's low, stable, is the one that you want to freeze. And so there's your 8 bits. There's 2 more, and there's 2 more. If you sat on the data bus right here, you'd see the opcode that they're executing for the entire cycle of the amount of cycles that instruction took. Does anybody have questions so far? Am I going too fast or not explaining clear enough, or should I speed up? We got a lot more stuff. This is old stuff. Okay, so saw a cool chip from Fujitsu. Anybody here use Fujitsu chips? No? So it looked like a mess. They did some weird stuff, but look again, microcode right here, or PLA, whichever it is. And here's the bus lines. But what threw me off when I looked at this the first time was the bus lines nothing came in from the bottom of the chip right here. And then the only place I saw the data bus come in was way out of, it's not in this image, it's way out of view on the left. The 8 bits came in. But then I looked at it a little closer, and I only had one of these chips to look at, so I couldn't strip it down. But what I could do is image it high res now and then rebond it and power it up and work with it. And so I imaged it high res and studied it. And what I was able to study was that this was basically laid as rows, 8 rows across the chip in the area of the core. And so in these rows, each row was a bit weight, D0, D1, D2, D3, D4, and so forth. And what actually happened was the bus line came in, went down to the bottom layer of metal, and came entirely across the chip and popped out here, and then popped out here, and popped out here. So all 8 bits popped out here, and meanwhile they interconnected at various points, what I'll call columns, for say data pointer register, program counter, register 1, register 2, whatever the architecture is. But the most important thing of the chip that makes this thing tick is they come up here, they trickle through, and then they plugged into 8 flip-flops up here. And then they had a nice line here that followed through the inverter that basically was always driven low. So hold it low, sit on the bus, eavesdrop the bus, and you walk the bus with 1 needle. So with 2 needles, you dump this chip, and you've dumped every other chip that I've spoke about so far today. Microtech is this Chinese smart card company. Microtech used the same exact flash that from TSMC, except TSMC said, oh, now we have filler metal on the surface, so it's more secure. Something like this they're going to probably be peddling. But I've already studied the flash on the older Freescale parts that you can buy, the 908 series of Freescale. And so you can see here the ordering of the flash. The chances that the user that designed into this TSMC process modified these lines is almost 0% possibly. So here's that die, and here I've marked exactly what to do. So I've said, okay, it's 25 to 27 spaces over from M3. I don't know really what I mean there actually, but I think I don't know. Anyway, so and then right in this box is where I want to dig, and what's under there is data bus bit 0. And so I made an assumption here because when I had stripped it down. This is a stripped down chip, but I didn't polish it. So if I had polished it with a lapping machine, I could get rid of all the oxide here and make this look smooth as can be. Just some notes on the chip. There's that filler again. It's everywhere. Here's some dark images of it. I'm just looking for the bright image. So here's a delayered chip, and we've got a huge flash here, 128 kilobytes. We've got 2 huge static RAMs. We've got 2 small static RAMs. This should be the 256 internal bytes. And then we have a boot ROM. So there's a ROM right here. Well, guess what? I'll bet you money that they boot from this ROM, and then they check the flash for like FFs or something. And if they see FF, then they stay on the ROM and they let you download or upload to it. Read or write to the flash. Very poor instantiation of a security measure. This is supposed to be a smart card. Remember. So here's the ATR coming out of the chip from what this went to. And so ATR is coming out of the chip, and I'm just sitting there with a needle down on D0, and I'm taking the other end I'm not even using a buffer. and I'm taking the needle, the end of a coax line, and I'm shorting it on ground. And so it just literally like this as it's resetting. And lo and behold, all of a sudden on reset 3B, the ATR changed. Well, guess what? That was the bootloader ATR. And so I glitched it back into the bootloader using a simple, my hand with a probe in my hand. It's crazy. But this is a secure smart card from a Chinese manufacturer. So, sorry? It is ASCII. This is actually a Dreambox clone chip for the Dreambox free-to-air receivers. So this was some Dreambox smart card chip that the Chinese had put in for the clone of the real Dreambox receiver. And so, just actually, I did this in about 5 minutes after I was playing. Once I exposed D0 in 5 minutes or so, I got it, and I couldn't believe it. I was laughing because I was in the middle of another job, and this was just like I was just playing around. You could see here like the older smart card chip. I'm going to speed up, guys, because I've got like 8 minutes, and so I'm going to actually skip a couple things. Before we spoke about dark field, here's the corner of that boot ROM and that 8051 from 1983. That's dark field. Here's bright field on the same microscope. So just flick a switch and it switches the mode. So bright field, you can't really read the ROM. You can't really see the bits. Switch to dark field, boom, now you can see them clear as day. Things have a purpose sometimes. I built up a lot of junk and I always find a use for it. So, because the optical microscope today is not that good. I use a fib today like crazy. And so like the 66 PE, I'll polish them down using a lapping machine. So I'll strip off a layer. I get all that oxide residue left. The metal floated away, it's gone. And I make these images on the fib after I polished it. So I polish them down until the actual metal is exposed to the air, to the atmosphere. Now, if this was copper, which it would be if you're at 45 nanometers or below 130 below, you're going to be copper. This would oxidize within time, unless it's in like a vacuum chamber, which it wouldn't be permanently. So here's the actual core to the 66 PE that I was after to study. Now, what's interesting on the fib, if this had been in a SEM, these lines would all have been white. They would have been white. But the fib's giving me voltage contrast. So this is telling me that these lines have been disconnected and they came from the surface. They came from up above on the upper metal layer. And so I polished this thing so smooth that you can still see, these are the vias where they made a connection before. So does anybody do this kind of stuff, like polishing chips? I know you do, Karsten, but does anybody else? No? This is a process that it's pretty fun, but you take a bunch of chips, you strip them all to the same level, and then you practice. You could build your own polisher too if you really tried. The liquid is really what you need to get, which is about $100 for a gallon of it. Here, if they had made microcode changes to the 66 PE, I would have seen it in this table. This is one of the instruction tables. The 66 PE, as I've discussed when I did the TPM attack, runs on microcode. And so it's kind of their doom. Now the bus scrambling I spoke about earlier, nobody's doing that anymore. They're doing it maybe outside the core, but in the actual central nervous system of the chip, the CPU is almost never scrambled, and I don't know why. Here's the metal 2 layer of that same area. So now in Photoshop I can stack these images, and I'm running out of time, so I'm going to try to find that fast. I'll find that last. So another cool thing in the fib, you get a chip like an ST with a mesh. I can drill down a hole. This is all tungsten residue right here, or platinum residue. I have both metals in my fib. So I drilled 8 holes and touched the bus line. The bus line is running exactly north and south on this picture. So from the top to the bottom, it's running down the chip. So I found isolated where the bus line was with a reference right here, but it's out of view kind of. But right in here, that's a hole that I dug to see where are the lines down on metal 3. I use a chemical called xenon difluoride in the fib to do this without hurting the metal. So drilled 8 vias down, touched metal 1, and then filled the via to the surface with platinum, and then made little donut rings in platinum as well. And so then I had to isolate them because these would have been shorted out. So then I used that same xenon difluoride gas, and I very carefully milled boxes around them. And it's black because it's an insulator again. The tungsten's been removed, and this is the oxide. Where here, this is like a spray can when I'm using the tungsten deposition. There's overspray always. So that was called a cleanup. Here's some random chip that didn't have good grounding. Atmel Mega 8. Anybody use a Mega 8? Nobody? Okay. The poly, not a very good. I need to practice when I'm polishing the poly. ST Thompson 350 nanometer process. It's used for like Nagravision, people around the world, GSM SIM cards. Not secure, but people have to focus to break it. This is again polished, not perfect, but good enough for what I was after. So you can see like an overall mosaic I was starting to make of the chip. So these are 1, 2, 3, 4, 5 across. So this would have been 5 across by somebody down, just to give me an overall mosaic in the fib. It's kind of I just did it because I could, but I didn't actually stitch them yet. Just no time. And so I was going to discuss this stuff, but there's not enough time to really cover it. The ST mesh, even today, I just did this last week with Karsten Knoll, make a nail polish mask, boom. It's in the wired video, you can see it. The mesh is gone. The chip's alive if I repair the mesh, if I jump it. Here I'm focusing on the mesh, the actual top metal itself to show you. And here I'm focusing on the actual lines down below. There's 7 to 6, mesh is out of the way, hit it with a laser and touch the bus and it's no problem. Get into newer chips, 180 nanometer chip, same technique, nail polish attack, boom, I just did it. Did it with Karsten the other day. The problem was that the nail polish, it flaked off or something from too many rinses and etches. These are very small timed etches, like 10 seconds, 15 seconds. You dip it in, a drop of hydrofluorics going down here, diluted for 15 seconds. Rinse it, check it. Do it again. Rinse it, check it. And the hot plates, it's slowly breaking down the nail polish along with the HF2. But you can see here the lines below. And this chip will work if I jump the bus. There's no reason it wouldn't run still. With the Thompson, remember, I only have to bridge one line. So here's a Thompson, brand new K7. This is the exact same chip Nagra 3 uses. That's why I don't understand why it's never been broken, except that the hackers are lazy maybe. I don't know. Or the Canadians are I don't know, maybe the laws changed in Canada. So here you can see I dropped tungsten across here, and this is a tungsten deposit. You can see the overspray, and it's so far out of the way I don't need to clean it up. And so this is connecting the mesh line from here to here. I went this is overkill. I didn't have to do it like that. And it gets even better. I can really just go to the end of this mesh line and just jump it to VCC. Even today, the latest Thompson chips, the latest 180, 150 nanometer chips only have to be tied to VDD, whatever the input voltage is to the core. They give you some give you like a fake oscillation, but it's clocked by a digital circuit, and that digital circuit samples that waveform when it's high. And here, after I did this bridge as a test, I ate through the mesh. These are 8 random lines. They're not the data bus. I don't know what they are. I just was doing it to show you guys. And then if you want to know how small that really was, it's here. So you can see, oh, I'm sorry, it's here. It's here. It looks like a speck of dirt. It's so small. And so here's the bridge, and here, this is optically looking at it at 1,000 power, and here's the hole I made. It's so tiny. And then here's the edge of the chip that says K7 something. That 7 means it's 100, well, no, it doesn't, I'm sorry. If you reference this code back to the chip, it's an STW, so this is actually 180 nanometer. STN is 150 or so. Does anybody have any questions? No? I do need to show you one thing though before you go. Okay, one question.
Do you have any software that you're using to automate the analysis of the imagery?
It's something I'm working on, but I don't. I actually do this all by hand, which is crazy. But I'm working with Karsten up here in the front row, and he's got a nice set of tools out there that can help me to automate it. And there's various other programs that can help automate it too. I didn't even, like ST23 is 90 nanometers. Here's the ROM of one. You can see the ROM bits there, clear as day. But I literally will typically do this by hand. But if I'm going to image a ROM like this, I need to do it automated. There's no way I can sit there. And I'm also going to assume that the ROM is encrypted. So I want to get an image of it, and then I want to study how it drives the addressing scheme, and then where the bus goes as soon as it gets into the core, where's it going to go? Here's another picture of that 90 nanometer part. 90 nanometers is a pain in the butt, so I don't even want to know what 45 is like. And this is a mesh that they're trying to give another impression of. Does anybody else have a question? Can you come to the mic?
I was late, so apologies if you already addressed this, but what about the SLE78? Is that something you're working on?
I haven't seen any. If I saw some, I'd love to see some samples because I have a feeling it's not as secure as they're claiming. Things never are. Even the 88. I can't really work on the 88 though because I had an NDA with them like 4 years ago. That's the only reason I don't talk about the 88. But the 78 is going to be something like the 88, which is like a dual rail type infrastructure. But what happens after the checksum? I mean, like it's so funny. Infineon came with a comeback about me, and they were like, "Oh, the opcode is never in the clear." Well, that's BS. Anybody that designs CPUs knows that somewhere in the core that instruction's in the clear. So what's going to stop? What's going to need to happen on an SLE78 is first they got to produce them, and if they're being produced, I haven't seen any used yet. In the GSM SIM card market would be the market to take it, and so I have seen the SLE76, but it's not a 66 type processor base. So the 78, you'd have to strip it down. You'd have to identify these two blocks, and then you'd want to disconnect the check of did the two compare. So disconnect the comparator and find the clear data bus. I mean, the opcode has to be in the clear at some point. Another thing that's interesting is the 66 PE. They claim it's out of the field, but yet I found PEs that are newer than the PE that the TPM used and the Xbox used. And they actually have done a complete redesign, and they've put the power plane on top metal. And for the GSM SIM card market, there's no active mesh on the surface. So any tests I need to do on it, on a PE, I would do them on this one now. But it just happened way later in the game. If you have samples and you can give me one, I'd love to see one. But of course, you probably can't.
Exactly.
So
thank you.
Yeah, no problem. So here's the money shot for that 2560 chip. Here's a freebie to anybody that wants to hack it, because Atmel is not in my good graces. So, so you want to dump an Atmel 2560 AT Mega? You just these two lines, hold them low. Take two probe tips, put them on the line. Capacitance makes no issue because these signals don't oscillate. They just simply power up static. These are being driven by single cells of double EEPROM. And these are basically lock bit 0 and lock bit 1 of the chip. And so it's kind of cool. And this was just used as an example of breaking a chip or So anyway, anybody else? Well, thank you for taking sticking around for this.